The Nernst coefficient goes like carrier mobility times the difference in the hole and electron thermal powers with opposite sign usually, so that adds. And here they're nearly canceling, so this is an easy way you can get a ratio that's diverging, and it seems like a sensible explanation. So the implication is that we've got very large hole and electron partial thermal powers that are nearly canceling in the thermal power, which I'll now show you, and it looks like there is some motivation for this scenario. So here's that sample C. As I said, it's fairly linear and modest in magnitude, but this A2 has a hump at low temperatures, and this A1, which actually is the same crystal measured after a period of time, has an enormous thermal power. This is rather unprecedented for a metal if it's phonon drag, but that seems plausible that it looks like a phonon drag. They usually show up at low temperatures. The difference between all these samples has to do with the oxygen content. At least that's part of the story. We can't actually measure the lithium on the individual crystals yet. It's pretty tricky, and you have to destroy them possibly. So we may try to do that, but at least we found that the oxygen content of these samples, and especially their CLAS constants, do differ in an approximately systematic way, although there is a bit of clustering here. So there may be two issues in the stoichiometry that we don't have full control of. But the basic idea here with regard to that two-component scenario that I suggested is that at oxygen, fully oxygenated, or at lower oxygen content up here, we have nearly perfect compensation, so the thermal power is small, the Nernst coefficient is as big as it gets, and then somehow as we, if you can add oxygen, some of the crystals with more oxygen have very large thermal power, suggesting that the compensation is incomplete, and the Nernst coefficient actually comes down at sample A2. So at least based on two samples, it looks like a plausible scenario. So let me tell you just a little bit more about the transport stoichiometry connection, because we've also measured the Hall coefficient, and I've collected other such measurements from the literature that may even give a little more impetus for this two-component scenario. So one thing that is true in the literature is that the conductivity ratio, so the next least conducting, the C, over the most conducting, varies quite a bit in the literature. So the largest numbers are 50 to 100 or so. That would be, again, Nigel Huss's group in England. The lines here, that's on the high end, about 100. Here's my crystal C, and that one's in the 50 to 60 range. And then I also measure this A2, that's quite a bit smaller. It's more like a 6 or 8, and these other groups have measured 3 to 5. So some of this could be the challenge of measuring a 1D material, making sure you have current flow along the right direction. But John's group's been pretty careful. They've done Montgomery analysis of this, and they've also done some oxygen annealing or air annealing of their samples and found that the resistance changed. So there is an incentive or a motivation to think that some of this may have to do with oxygen stoichiometry. Here's the thermal power, but now I've added this plot of the low temperature thermal power as a function of the C parameter and the high temperature thermal power, and here they all are together. So at room temperature they nearly have the same thermal power, but at low temperature this other thing shows up, and that's just another way to display that. Here we've also extended the thermal power to higher temperature on one of these samples, and just to convince ourselves that it's going to continue with the linearity and the fact that it becomes negative. So that tells us that the diffusion thermal power, unencumbered by all this stuff down here, whatever that is, looks to be negative. And that may figure into our discussion of the Hall coefficient. Now, why the C parameter should matter? Well, at least qualitatively, here's a view of the chains and how they're oriented in the unit cell. And you can see that if the C parameter is growing, that it's probably going to have some influence, especially on these interchain coupling parameters. Only recently, some of the theorists have started to look more carefully at this system and have done a tight binding analysis to put some constraints on these parameters as they see it, at least to fit the Fermi surfaces. And they've also talked quite a bit about the correlation effects. So I refer you there on those things. I should mention that, I mentioned.
It's been a nice week. It's especially nice to tell you about this project because it was really born here in Brazil. And I'll tell you a little bit about that in a few minutes. There's a project that I started together with Carlos dos Santos. And there's a number of people from my group, and there's some people from Germany as well who've been working on crystal structure studies. Hugo Sandin from Lorena provided the crystals for us, and I'll tell you a lot about those. And then we've had some collaboration too with some people at Los Altos helping us out with various measurements. So first of all, what prompted us to study these metals, which you would imagine have been studied inside and out through the years? And the answer to that is a cup of coffee. So Carlos and I one day were sitting down together over coffee, and I just asked him, what do you guys do down there in Lorena? And he told me, well, we've been for many years refining these refractory metals like niobium, because Brazil is the world's largest producer of niobium. And so we've developed a method for doing this, and we've been selling niobium around the world. And then I just asked if there were single crystals available, and Carlos said, yes, there are. And I said, well, why don't you get one, and then we'll just study its superconducting properties. And that's really how this project started. Back, I think it was in 2005, so it's quite a while ago now. So here in this talk, I'm going to tell you about the refining of vanadium, niobium, and tantalum. And this is really the born in Brazil part. Really very fascinating. So for those of you who haven't seen this, I think you'll really enjoy it. How the single crystals are harvested, that's fascinating too. Tell you a little bit about how we measure thermal expansion, which I did already on Monday, so I'm going to give a very shortened version of that. And then talk about our results, which basically are that vanadium, niobium, and tantalum are not cubic at low temperature. I'll show you the effects of impurities on this structural phase transition. And then I'll just tell you about a connection, a possible connection to the A15 superconductors, which is a very surprising piece of the story. I also should mention it's nice having Brian Abel here today, because back when I was a graduate student working in his group, one of the first projects I had was studying niobium. So I've come back to niobium again after so many years, which is really quite interesting. So this is just a real quick condensed version of refractory metal refining in Lorena. And the idea is that they wanted to try and capitalize on this natural resource and provide really or produce really high purity metals and sell them. And eventually transfer this technology to industry. So there was a group of researchers from Campinas that came to Lorena under Professor Pinati to launch this project. They started off by creating, you'll see, a mixture of niobium and aluminum oxide, which is then further refined. And then they commissioned the construction of a furnace, and I'll tell you about this furnace in a few minutes. And then they first started processing these ingots. These ingots are huge. You'll be very surprised at the size of them. And eventually, by 1990, they had refined over 100 tons of material. Niobium, titanium, tantalum, aluminum. Huge amounts of material. And then eventually this technology was transferred to a Brazilian company, so they have two of these furnaces now, I think somewhat larger power. So here's a picture of the furnace when it was commissioned and tested in Hanau. The furnace, part of it actually extends down below the floor so you can remove the ingots. And those who are in Lorena have seen this before. And here's Professor Pinati here. So they start off with niobium oxide, and then they do a reaction, which I'll show you in a little while. It's an exothermic reaction, looks very exciting. Produces niobium and aluminum oxide, and then they E-beam melt this, electron beam melt it, And that volatilizes the aluminum and aluminum oxide, outgasses the nitrogen and oxygen, and removes carbon as well. And all of this is sort of trapped out on water-cooled copper panels inside of the furnace at high vacuum. So this is kind of an idea. This is the starting material after this reaction here. It's fed into this furnace. There's dual electron beams that melt it. It drips down into a crucible, and that rod is drawn out through the bottom during the process. There's multiple drip meltings that are done. They first start off feeding these things in on the side, and then a second and third melting where they feed it in through the top to refine it and purify it. Carlos and Hugo back in July during my first visit here to Brazil. So the furnace, you get an idea of the size. Here's the 2 electron beam guns up here. This is 3 kilowatts. You know, it's a really big device. These rods, amazingly, are rods of high purity niobium. These things are huge, you know, really huge. So these rods of niobium have been completed through this refining process. I don't know how much they weigh, a few hundred pounds. This picture, for me, is really amazing. If you take one of those rods and slice it along the length, and look at that slice, which is right here, you'll notice that there's this grain boundary here. That's a single crystal over here. That whole side is a single crystal, and there's another crystal on the other side of that grain boundary. So